All right. So Math 222 shifts gears at this point. We have been talking about exponential functions, logarithmic functions, other sorts of transcendental functions. We've been doing derivatives and integrals. Now the course changes gears. Now we start talking about various techniques of integration. So the next bunch of lessons is about different ways to do different types of integral problems. And so we begin with integration by parts, and integration by parts boils down to the product rule. The product rule, you will recall, says that if you have the derivative of some product, u times v, well, that's u times dv dx plus v times du dx. You remember this from Calc 1, which means, just a little bit of algebra here, there is nothing earth-shattering here at all. I'm just doing algebra. That's all I'm doing. Well, what I'd like to do is take the integral of both sides of this equation, dx. So we'll take the integral of both sides of the equation with x as our variable of integration. Well, what does that leave us with? That leaves us with the integral of u dv is equal to, well, this is the integral of the derivative of uv, that's u times v. And this is the integral of v du. And this thing is what is called the integration by parts equation. This is how we do integration by parts. It is so unapparent at this point in the video why this is important. So what this does is it lets us do integrals that are products, like this. The integration by parts equation came from the product rule. We expect to use it in product situations. So here's what we hope to do. We hope that some of this is going to be the u part, and we hope that some of this is going to end up, the dv part. We identify our integrand as being u dv. And then from dv, we figure out what v is. From u, we figure out what du is. And we see if this thing is easier to work with than that thing was. So you have no idea what the antiderivative of x sine x is. So we're stuck. What are we going to do with that? Well, what we're going to do with that is we're going to let this part be the u part. And then the rest of this is the dv part. So from u, we get du. If u is x, the derivative of u with respect to x is 1. The derivative of u with respect to x is 1. If dv is sine x dx, what v got us there? Well, minus cosine x got us there. Technically speaking, plus a constant, but that constant gets added and subtracted, so it drops out. We can use any constant that we like. We will choose to use 0. So what does integration by parts say? It says that the integral of u dv is equal to u times v minus the integral of v du. So in our case, u is x, dv is sine x dx. U times v, that's x times negative cosine x, minus the integral of v du, that's negative cosine x dx. So this whole thing hinges on, is that easier to work with than the integral at the top of the page? The answer is yes, so we're in great shape with that. So what happens? Well, we can do this. This is as it is. That's just what it is. This is plus the integral of cosine x. Done. Done. You can check. You can take the derivative of this thing and make sure you end up there. It works. Let's see about this. It's a product, and the product makes me think maybe this is an integration by parts problem. If this is an integration by parts problem, maybe this part is the u part, and maybe this part is the dv part. What makes this the good choice for you? Well, its derivative is easier to deal with than the other derivative, right? I mean, this has an easy derivative. This has an easy antiderivative. So it makes sense to use those in those roles. If we go the other way, if the u is e to the x and the dv has the x squared, then the antiderivative's got a cubic. Take the integral of a cubic, it gets weird. So we'll try it this way. The integral of u dv is uv minus the integral of v du. So that's the integral of u dv is uv minus the integral of v du. And so you ask yourself, is this better than what we had before? And the answer is yes. We still can't do this, but it's better. We've dropped a power of x. So we hope beyond hope that if we do this one more time, we're okay. So in this case, the new u is 2x. The new u. New year, new u. The dv remains e to the x dx, and we take derivatives and integrals, and we try again. So this is its own integration by parts problem, where this thing is uv minus the integral of v du. So our integral is x squared e to the x minus 2x e to the x minus a negative that's plus the integral of 2e to the x. Done. Problem solved. Done. And this works whether we're dealing with definite integrals or indefinite integrals. Observe definite integrals. The integral from 0 to pi over 2 of x cosine x dx. It feels like it's an integration by parts problem. This is a product, so we think maybe, so maybe this is the u and maybe this is the dv. And that's sort of confirmed when it's easy to take this derivative and it's easy to take this antiderivative. And so the integral from 0 to pi over 2 of x cosine x dx is uv minus the integral of v du. But there were bounds here. So we do this between 0 and pi over 2, and we do this integral from 0 to pi over 2. So what is that? Well, this is pi over 2 times the sine of pi over 2 minus 0 times the sine of 0 minus the antiderivative of sine x from 0 to pi over 2. So that's pi over 2 plus cosine of pi over 2 minus cosine of 0. Done. You get a numerical answer. I'm going to throw in an OYO here. I want you to do a couple of things just to check your understanding. I want you to try this one and I want you to do one with a definite integral also. I want you to do one with a definite integral. We'll see about that. We'll talk about those when we gather in class. I intend to go for about another 6 or 7 minutes here. So if you need a pause to reset your brain, take one and then hit the next 6 or 7 minutes hard because they're important. Sometimes it's an integration by parts problem when it doesn't look like an integration by parts problem. This is not a product like the others were products, but this has the added advantage of I don't know what the antiderivative of this thing is. I know what the derivative of this thing is. So we make this thing the u in an integration by parts problem. This thing becomes the dx. It's worth a shot. We know what the we know what the derivative of ln x is. I'm so sorry. Calculus is already hard enough. The du is 1 over x dx. The antiderivative of 1 is x. So the integral of u dv is uv minus the integral of, well, I'll be. I know how to do that. So what does that help with? That helps with the questions that would lull us to sleep. This one lulls us to sleep, right? Because this is always our u, except then we got to remember what the antiderivative is for this thing, and forget that. I'm not doing that. So instead, this part is the u, and this part is the dv. Wait a second, coach. You said that we shouldn't do this because then the antiderivative is this ugly sucker. Yeah, but that's better than the antiderivative of that ugly sucker. And think about what VDU looks like. It's like we planned it. UV minus the integral of VDU. Is that integral better than the one we were dealing with? Yes. Yes, it is. Done. Done. One more. You've been doing great. You've been doing great. It's a product of unrelated things, and so we think to ourselves, this is integration by parts. Maybe this is the u, maybe that's the dv, it's worth a shot. The derivative of e to the x is easy to find. The antiderivative of sine x is easy to find. So the integral of e to the x sine x dx is uv minus the integral of v du. I'm going to pull this minus 1 out. And I ask myself, is this better than what I had? And the answer is, it's not worse. So maybe trying this again is a decent idea. And so we run our own integration by parts inside the red brackets. This time we'll run the same idea where du is easy to find and v is easy to find. So inside these parentheses, we've got uv minus the integral of v du. Well, that doesn't seem good. That seems terrible. That seems terrible. Like we're stuck in an infinite loop. Here's the thought. I maintain that you have enough information here to finish the job without doing any more integration. You do not need to do any more integration to finish the job. But I don't want to talk about that here. I want to see what you think when we gather in class. And so that's what I'm going to do. I'm going to leave you in suspense. In volume 2 of our textbook, so now we've switched over to volume 2, in section 3.1, you're looking to try your luck. Oh, you're looking to try your luck. And I hope it comes out well for you. All right, we'll see you in class.